Okay, so in the last session we were discussing about, we have just started about the application of elastic behavior of materials. Okay, so we had done a, like we were talking about the crane problem, and then how a crane is used to carry heavy weights and to move heavy weights from one place to another. How a crane consists of a pulley, a rope, and a hook and all. So how it carries a weight of say 10 tons, which is equal to 10,000 kg, that you have converted into Newton by multiplying it with G, and then by doing the force by area of the rope. Area of the rope is nothing but pi by 4 d square. So you have compared the strength of the steel, which is the made rope is made of steel. So then you find out the diameter of that, because the strength of steel is equal to applied stress, right?
Yes.
So applied stress should not be more than strength. So maximum it can be equal to the strength. So applied stress is equal to weight that is being applied, that is 10,000 Newton, which is 10 tons, which is 10,000 kg, into 10, which is 1 lakh, let's say 100,000 Newton, into that divided by your area of cross section, which is equal to, let us say in that case it was some 400 MPa or whatever. So you need to be careful about the unit. Okay, then we have arrived at a diameter, then we got it as a diameter of a rod. Then we thought that, okay, rather than having a rod, if we have like steel ropes, then braided into a rope, it will be more rigid and it will carry better load. So that we have done. So that is more related to longitudinal load. So this is an example of a longitudinal behavior. Okay. What is longitudinal load? When your load is acting along the length, it is perpendicular to the cross section, but along the length. So this is a rod, the load is acting along the length. But there are other examples where the load can act perpendicular to the length of the beam. So this is called a rod, these are called a beam. So these are example of, I was discussing about examples of different kind of structure. For example, this is a building. Okay, so in a building you will have beams and columns. So the horizontal members are your beams, the vertical members are your columns. Okay, so on this, so you can see so the load, so there is a roof on the building, you can see. So the total load, the self weight, the weight of the upper higher story, multi-story above it, and also whatever number of people that is going to carry, and so there will be some kind of load for which the building will be designed. So that particular load will be transferred by the beam to the columns. Okay. Then we were discussing that these columns are made of concrete. So these columns will be taking compressive load. So like this is your column. So this load will come as a compressive load if it is a free body. So it's the concrete is being used because its compressive strength is very good. Okay. So as compared to its tensile strength, concrete cannot take tensile load. It can take very good compressive load. So these concretes, I was also explaining that if you take a concrete cross section of this column, you will have something like this. Then you will have concretes. In between concrete, it will be reinforced by some kind of steel rod. So that is called a reinforced concrete structure. Okay. So you will have concrete, and it will be reinforced by some steel rods. If you take a cross section of this column, you will get some, maybe it is a rectangular cross section. So you will have concretes, throughout you have concretes, and then you will have some steel rod in between. Okay. So you will have steel rods to reduce the area of the cross section. You have stronger steel rods in between. Okay. Yes. So you might have seen during roof casting and all, there will be steel rods are being used. Similarly for columns also, steel rods are being used. So you need rods. Okay. So rods are required, concrete is required, sand is required, cement is required. So all those things. Cement is a binding agent. Cement, what does it do? It binds the concretes together, So sand and concrete, those things will, cement will bind them together. It is kind of a binding agent. Okay. So that is for buildings. Similarly, you can see a bridge. So let us say this is one side of the bridge, and this is other side. This is one side of the bridge. This is other side of the bridge, and this is the bridge, and this bridge is being supported at different locations. Like these are different columns. Okay.
Yeah.
So if the total length of the bridge is 3L, you are dividing it into L, L, and L. So you are reducing the span of the bridge. So why you are reducing? Because if you don't have this column, it will sag like anything.
Yeah.
You don't want it to sag. And in case of a beam, what kind of load it will take? Its own weight it will take, traffic weight it will take. So and vehicle weight it will take. All that it will take. So it will be designed with some factor of safety and all that.
Yes.
Okay, so that it never collapse. Okay. Then we told that okay, these are my beams and these vertical members are my columns. So in addition to these load like own weight and traffic weight, there will be some kind of loads like on these columns there can be some wind loads. Okay. Heavy wind is blowing. That means this column a long member. Even if it has a strength, there is, you might have seen these thin people, thin people, we call it as slenderness ratio. Slender, very slender member, it will bend actually, it will buckle. Slender member will buckle. So that is called buckling phenomena. That is a instability phenomena. That also can happen. Okay, so that is a columns can buckle, long columns can buckle. That is another thing. Okay. So then just to give you a feel like what is the span of the beam and how does it deflect and all that. So let us have a beam of span L. Okay. Let us say the total weight uses, it is a uniformly distributed load throughout the bridge. There is a load. Just imagine that it is concentrated at the center. If it is concentrated at the center, then what is the deflection? It is PLQ by 48 EI. Actually, it is WLQ. Okay, P or W are same here. Okay, the load. Okay. So this deflection is directly proportional to cube of the length. Okay. So this deflection is directly proportional to cube of the length, and it is inversely directly proportional to LQ. Right. So if you reduce the length, your deflection will reduce drastically, and it is inversely proportional to moment of inertia. No, it is inverse. So it is inversely proportional to EI. Young's modulus and moment of inertia. So if you increase the Young's modulus, that means if you increase the strength, deflection will decrease. If you increase the moment of inertia, deflection will decrease. So this moment of inertia I was telling for a rectangle, moment of inertia is otherwise called as second area of moment. A second moment of like area into distance square. Okay. So it is second moment of area. Okay. So the moment is equal to force into distance. Here it is like area, this thing. Like say for example you have A by 2 here, A by 2 here. Like say this kind of a structure. And let us say this is H and this is H. Okay. H. So the moment of inertia of this structure will be like this. Moment of inertia. I think moment of inertia might be there in your 11th. I'm not sure.
In that center of mass.
Yeah. So there it will be there. So moment of inertia will be A by 2 into H square plus A by 2 into H square. That means you are squaring the distance. Okay. So it will become H square into A. H square will become common. Okay. Then A by 2 A. So this become A. So H square. Okay. So H square into A. So like that. This moment of inertia is see, it is mass moment of inertia is also there. See, if in place of area, if you are writing is mass m by 2. So it will become mr square. Normally moment of inertia is mr square. You write moment of inertia is mr square. In moment of inertia, 11th you might have studied. Mass into distance square is moment of inertia.
And so torque and all comes in there.
So mass into distance square. So in this case, this mass is nothing but your area into density, right?
Yes.
So you forget, think that it is uniform density. So neglect density. So only thing, so area and so mass is equal to volume into density. Okay.
Volume is equal to
Volume is equal to area into thickness.
Thickness.
So you ignore the thickness, ignore the density,
Okay.
it will become A square. So in this case, your moment of inertia is bhq by 12. That is area
For
moment of
rectangle.
inertia. Your moment of inertia is not mass moment of inertia, but it is area
Area
moment of inertia, which is bhq by 12.
because it is acting on a surface area.
Yes, right. So if we decrease, if we increase the height,
Then
then
deflection
deflection
will
will
decrease.
decrease. So that is the means take away from here. If you decrease the increase the depth, then it will be good. So another thing is that like you have seen in railway when your railway wheel is running on that rails, okay.
Right.
So those rails are of like say
I-shape.
so this is your let us say this is your rail, okay. So if you take a cross section so your rail, if you see from the side, it will look something like this, right? It will look something like this, right? It will,
Yes.
from the side it will look something like this. But if you take the cross section, so how does a rail cross section looks like? The rail cross section is a I cross section, okay. So the rail cross section is a I cross section. It is not a rectangular cross section. What is the reason? Because for the same area, for I cross section, the moment of inertia will be more.
Oh, so
Okay, so actually what is happening, what you are doing, let us say here area is 10 mm square, a 100 mm square, let us say this is 10 by 10, okay. Let us say this is 10 by 10, so 100 mm square is my area, okay.
yes.
So the same 100 mm square, what I will do, I will put let us say like say 10, let me say I will put 40 and 40 here.
Yes.
40 here.
Yes, yes.
So I will make it as let us say I will make it as 20 say let us say I will make it as 10 by 4. 10 as width and 4 as height.
Yes.
10 by 4 I will make it here. 10 by 4 I will make it here.
Yes.
80. Then remaining this much will become say 20. Like say this thickness is 2 and height is 10. So this I will make as this height as 10. This height as 10 and this one as 2. Understood? No? So if I make it that same 100, instead of making it a rectangle, I have made it as a I section.
I section.
So what will happen here? The moment of inertia will increase. Because what happens, the more you keep the area away from this neutral axis, actually this axis is called neutral axis, the moment of inertia increases. Because more and more area we have moved away from the neutral axis.
Understood.
Because your moment of inertia depends on the distance of this section from this axis. If this section
Is away
more
from
and
it.
more sections are away from the axis,
Moment of
moment of
will be
inertia
more.
will increase. Because here the motor movement is coming. So movement is always associated with a distance.
Yeah.
So what is your inertia? See, you have studied inertia.
Yeah.
So a bulky person, he has more inertia. Right? A heavy person, he has more inertia. Right?
Yes.
A thin person will have less inertia,
inertia.
because a heavy person, he is moving at a big high speed. That means it is very difficult to stop him. Right?
Yes.
So a heavy person will have more inertia. So what do you mean by inertia? Inertia means more
The state
mass
of-
or something. So moment of inertia means
The
moment
distance.
of the mass.
Distance.
Okay. So moment of the mass means what? Like you know that you know torque. So you know a force F is acting here, and the distance is d, right?
Yes.
The distance is d. So F into d is the torque or the moment.
Yeah.
So that is moment. Okay.
Yeah.
So a distance. Similarly, moment of inertia is something like this. So let me say this is the distance r, and here I have a mass m.
Yes.
So
yes.
moment of inertia is
M.
m r square. Okay. So here inertia means that mass is inertia, and moment here is second
Distance.
square of the distance.
Distance.
Okay. So the moment of inertia for the I section is very high as compared to a rectangular section,
section.
because the inertia means the mass is same.
But the distance.
See, for this area and this area is same.
The distance
So mass is
The
same.
distance from
Only
that
thing
axis
is that you are moving more and more mass away from the axis.
axis
That's why the moment of the mass is more.
more.
So it is moment means second moment of
That
area.
square of distance.
It is moment of inertia is second moment of area, not first moment. See, F into D is torque is equal to torque or moment is equal to F into D, right?
Yes.
So this is first moment. But area moment of inertia you can also call it as M into D square also, whatever. This is second moment. Okay, second moment of area.
Understood.
So instead of mass you are telling it area here. That's all. That is the only difference.
Yes.
Okay, so for this kind of load where it is going to bend, so here it is bending, it is not extending. You are not extending it.
Yes.
Instead, see what is bending? This is bending.
Yeah.
Okay, but you are stretching
Extending it.
This is extension. Whereas I am putting some load
Deflection,
here.
if you are
Transverse load I am putting here.
if it seeps
That means
down.
it is getting deflected.
Yeah.
So it is getting deflected. Okay, it is getting deflected. So when this is happening, it is called bending.
Yes.
Okay, so this is bending. Now when the transverse load acts, the bending comes into picture. Okay, so this is the main region. Like if somebody asks you why you want I section in a rail beam or any
Increase moment of inertia.
bridge or anything, because the moment of inertia is high, so deflection will be less.
Yes.
If the moment of inertia is high, also the bending stress will be less. Everything will be good in if the structure is subjected to transverse load,
Yeah.
a load perpendicular to the length of the
Length of the
structure.
structure.
Better to use a structure with good moment of inertia.
inertia.
Okay, so you can take a picture. Just in another 5 minutes we will finish. Okay, so. So the use of pillars and columns is also very common in buildings and bridges. Okay, so a pillar with rounded edge is shown. Rounded edge supports less load than that with diamond shaped ends. So the precise design of a bridge or building has to take into account the condition under which it will function, the cost and loading period, reliability and usable material, etc. Okay. So the answer to question why the maximum height of mountain. Okay. So we'll now in column there is one example they have given, like so you have taken the picture.
Yes.
Right? So in case of see, I am repeating it. So the more I repeat, the better it is, because if I teach you 3 times, it should be there in your mind. Okay, teaching once, teaching twice, teaching thrice, it should get like you should memorize it, right?
Yes.
So now you understand why we want to increase the moment of inertia, right?
Yes. Yes.
Okay. So moment of inertia, just remember it is second moment of area.
Okay.
First moment of area and second moment of an area. So that was mr square. So area, density and thickness just you have ignored and it has got converted to area. So it becomes area moment of inertia. Another is mass moment of inertia. And they are telling that the use of pillars and columns is very common in buildings and bridges. So they are telling that if you have a column like this, and if you have another column with some diamond shaped at the end, this will have better load carrying capacity. So that's with a distributed shape at bridges. A pillar with rounded edge as shown in figure 9.10a supports less load than that with a distributed shape at the end. So This is rounded shape, this is distributed shape, this will carry more load. That's all.
Yes.
So that you can easily understand because the area is gradually increasing there.
Yeah.
Okay. So it will take more load. Okay.
Understood.
That is one common. You might have seen like when you observe the bridges, you have seen those columns. At the end, there will be sudden increase, gradual
at
increase
the
in
end.
the area. It will increase the load bearing capacity.
Yeah.
The load bearing capacity that will increase.
the
Suddenly
end.
the bridge is sitting on that. So if you have a bigger area, it will have more load bearing capacity
Mostly
there.
at the end.
Okay. So we'll do one numerical, very nice numerical. Um, why a mountain is of certain height
Pyramid.
in nature, why it is pyramid shape, and how you arrive at the arrive at that height. The answer to the question why the mountain height of a earth on earth is 10 kilometer is 10 kilometers. So the question is why the height of mountain is max equal to 10 kilometer. That is the question. Then this is from law of nature. Why is it so? Okay, so you know Mount Everest. Okay.
Yeah.
What is the height of Mount Everest? I think 8,848 meter or so.
Yeah.
Something nearly
8
9 kilometer or
8
so.
to 9 kilometers.
Mount Everest. So something nearly 10 kilometer. Why is it so? That is the question. Okay. So the 10 can also be produced by conditioning. So this can be justified by studying the elastic properties of rock. Elastic properties of rock. Okay. So because the mountain is made of rock. Okay. So a mountain is under uniform compression, and this provides sense of shearing stress to the rock. Okay. To the rocks under which they can flow. Okay. So the stress yeah. So okay. So the stress due to all the material on the top should be less than the critical shearing stress at which the rocks flow. Okay. So at the bottom of mountain of height h, the force per unit area due to weight of the mountain is h rho g. Rho is the density of mountain rock. G is the acceleration due to gravity. And due to gravity, the material at the bottom experience this force in vertical direction, and the sides of the mountain are free. Okay, therefore this is not a case of pressure or bulk of the. There is a shear component approximately h rho g itself. Now the elastic limit of hope. So what is happening? You have a, let us say you have a rock. Okay, so let us say just we are imagining this is a rock. Okay, so let us say this height is, let us say
H.
Okay. So the load acting on at the bottom, just at the bottom. Okay. So here, let us say here there will be load acting. Let us say this is h by 5. Okay. So let us say this is another h by 5. Let us say this is another h by 5. Let us say this is another h by 5. Here whatever load is acting, that is only because of this much height. Here whatever load is acting is because of this much height. Here whatever load is acting is because of this much of height. That means the lower we go, the higher is the weight that is acting. Okay. So at the bottom, almost at the bottom, the highest load will be acting.
Yes.
Same thing as we have studied in the hydrostatics also.
In
H rho G we are
fluid
doing.
mechanics.
The deeper in fluid mechanics, the deeper you go, or a swimmer, he feels more pressure at the bottom
because
more and more this thing is there. So this H, rho and G. So this is the unit of pressure. Okay. So this pressure you will get this pressure unit as Newton per mm square. Newton per mm square or meter square or whatever you will get Newton per meter square, let us say you will get. Okay. So we know this pressure should not be more than the shear strength of the rock.
Okay.
This pressure should be equal to shear strength of the rock, strength of rock material, because it is compressing here. So when both sides are free, the same load will act as shear also, like whatever load is acting in this direction,
At that side also same thing.
because it has to be balanced. Okay, so this actually, when if you take any element, if there is a load acting in this direction, it has to be balanced like this, otherwise there will be imbalance. So whatever shear compressive load is acting, it has to be balanced.
So if it's
Otherwise,
acting
see, this will try to rotate it in this direction.
Understood.
So if you take a center point, it will try to rotate it in this direction. So you have to have a corresponding to this
so that
vertical
it
force.
remains at that position.
Corresponding to this vertical force, you need to have a shear balancing that. So so this H rho g is acting here. Actually, the load H rho g is acting as compression here, and there is a corresponding shear also here, H rho g. Okay, so that shear strength of the rock. So we are not comparing with the compressive strength of the rock, because compressive strength of the rock is more than that of the shear strength. The
Yes,
rock
yes,
is
yes.
very good in compression.
Compression.
So we should not take compare with the higher value. We should always compare with the lower value. So this H rho g we are comparing with the shear strength of the rock. Shear strength of the rock is very low.
More less than that.
Less than that of the compression. So
Compressive
so this pressure. So we know H. We do not know. Density of rock is given as 3 into 10 to the 3000 kg per meter cube. Okay, 3000 kg per meter cube. Okay, that is the density, and G you know 10 kg per 10 meter per second square, right?
Yes.
9.8 meter per second square.
Yes, yes.
Okay, so this is equal to the shear strength of the rock. Okay, so that shear strength of the rock. So typical rock shear strength is 30 into 10 to the power 7 Newton per meter square. 30 into 10 to the power 7 Newton per meter square. So which is nothing but 300 MPa. That's all. 300 MPa. Okay. So when you compare this, so what is happening? So this will become H into 3 into 10 to the power 4, right?
Yes.
And this side it is 3 into 10 to the power 8, right?
Yes.
So you will find it as H is equal to 10 to the power 4 meter, right?
Understood.
That means it is 10,000 meter,
Yes.
which is equal to, so H is equal to 10,000 meter, which is equal to 10 kilometer. So as the mountains are made of rocks, and the rock shear strength is
We should take
30
shear strength, not
into 10,
compressive
300 MPa. So we are not comparing with
Compressive.
we are compressive strength is sigma c. We are comparing with the shear
Shear
strength. Okay, tau allowed. Okay, of the rock, because compressive strength may be for, let us say, 400 MPa. So why we will compare with 400? We will better compare with 300. We will arrive at a lesser height.
Yeah.
So that is the reason in nature we don't find mountains of height higher than 10 kilometers.
Understood.
Understood? So that is the takeaway from here. Okay. So with this we come to an end of mechanics of solids. So we have studied so many things: Young's modulus, rigidity modulus, bulk modulus, Poisson's ratio, and we have
Energy.
studied stress strain curve, what is proportional limit, what is elastic limit, what is yield points, what is ultimate tensile strength, what is
Fracture
breaking breaking point. You should know each and importance of each and every point of a stress strain diagram of mild steel. And we have solved so many numericals related to
Young's
longitudinal strain, shear strain, and this thing. So and then we have solved a crane problem. What should be the diameter of the rope? And then finally a beautiful problem from the law of nature. Why the height of mountain should not be more than 10 kilometer? Beautifully explained. So you should understand how interesting is science if you understand it. Science is never boring if you understand it. You may get into sleep while studying literature, but if you understand science, it is so exciting. Okay, so science is never boring if you understand it properly. Okay, so with that we come to a conclusion on mechanics of solids. I hope there will be at least two numericals on this in any of your exam. Okay, so just revise it, go through my videos. If you want, you can share it with your friends so that they can also be benefited. Okay, okay. So thank you. Okay.